Hello friends, in this video we'll be learning about isomorphous phase diagrams. In my previous video we have seen how we construct an isomorphous phase diagram. In this present video we'll be learning about, by constructing isomorphous phase diagram, how to find chemical composition of different phases present in an isomorphous system. And the second one, the most important one, is finding the percentage of different phases using lever rule. Okay, so we will use a principle known as a lever rule in finding the percentage of different phases in an isomorphous system. Okay, so let's get into the topic. So for example, if you consider a binary isomorphous system, binary isomorphous phase diagram I am considering. Binary implies two components. Let us consider the two components are A and B. Okay, if I draw the isomorphous phase diagram, suppose I'm taking temperature on y-axis in terms of degree centigrade, and composition, that is the weight percentage of the alloying element, I am considering weight percentage of B. On the x-axis I am ranging the percentage of B from 0 to 100. I will get the isomorphous phase diagram like this. Okay, so this point indicates the 0% of B, implies this point will be the melting point temperature of pure metal A, and this point corresponds to 100% of B, implies 0% of A. So obviously this point corresponds to melting point temperature of B. So now by constructing the isomorphous phase diagram, so we will identify the different phases in this diagram. So above the melting point, this area will be liquid, and the phases in this area will be alpha plus liquid, and the phases in this area is alpha. So this identification of phases we have learned in my previous lecture video. So suppose if I consider a particular alloy, like this, let us consider the alloy composition is 30A and 70B, 30 weight percentage of A and 70 weight percentage of B. The considered alloy point is 70. Okay, so at any temperature, to find the chemical composition of phases and to find the percentage of phases at any temperature, I will construct or I will draw a horizontal line at the considered alloy point, like this. Okay, so from the considered alloy point at this temperature, I have drawn a horizontal line. Now this horizontal line intersects the two phase boundaries. This phase boundary is the solidus line, where the solidification will end, and this phase boundary is the liquidus line. Liquidus line indicates at this point solidification will start. Solidus line indicates at this point solidification will end. Suppose let us assume we are drawing two perpendiculars on the composition axis, and suppose let us assume these values are 40% of B, and suppose these values are 80% of B, right? So we are in a stage to find the chemical composition of the components in different phases. So this point indicates the solidus line. So in the alpha solid solution, which is formed at this temperature, for this alloy, we are having 40 weight percentage of B and remaining 60% of A. So at this temperature, we got two phases, alpha phase and liquid phase. So in the alpha solid solution phase, we are having 40B and 60A as the chemical composition. And in the liquid phase formed, we are having 80 percentage of B and 20 percentage of A. So thus with the help of a tie line, at any particular temperature, we can identify the composition present in different phases. Now our next intention is to find out at this particular temperature what is the percentage of alpha phase formed and what is the percentage of liquid phase formed. So for that, we will use a principle known as lever rule. So let us understand how we use lever rule to find out the percentage of phases present in an alloy at any particular temperature. So let us consider the isomorphous phase diagram which we are discussing. Right, so this is the isomorphous phase diagram we are discussing. Temperature on the y-axis in terms of degree centigrade, and composition, that is the weight percentage of B, on the x-axis. We have considered an alloy. Of composition. 30A and 70B. 30A and 70B. At any particular temperature, we have drawn a tie line, and we have finded the chemical composition. So this considered alloy point is called as a knife edge. And this horizontal line is called as a tie line. Okay. So now what does this lever rule states? So this vertical line divides this horizontal line into two parts. The vertical line divides this horizontal line into two parts, 1 and 2. So as per the lever rule, the vertical line divides the tie line into two parts. The inverse of its length indicates the percentage of phases, present in the alloy at any temperature. So let us understand this. So we have considered the alloy of 30A and 70B. So this point is 70. Now from this considered knife edge point, moving to the left, we got the solidus line. The region this region is alpha, this region is liquid. Now we have taken this point as 40 and 80. So let us represent these values here. This is 40 and this is 80. So this is 40 and 80. So from the considered alloy point, if you are moving to the left, you are getting alpha phase. Moving to the right, you are getting liquid. So percentage of alpha phase as per the lever rule is equal to the lever rule states inverse of the length is the percentage of phase present. So if you want to find the percentage of alpha, take the reverse length. Okay, so it is equal to 80 minus 70. From the considered alloy point, if you move to the left, you are getting alpha. The reverse length is This one 80 minus 70 divided by 80 minus 40 into 100. So if you simplify this, it comes 10 by 40 into 100. So it comes around 25 percentage. Okay. So at this temperature, for this alloy, the percentage of solid solution formed is 25, and percentage of liquid phase formed is, from the considered alloy point, if you move to the right, you are getting the liquid phase. So the opposite length is this one. So it is equal to 70 minus 40 divided by the total length. This is the total length. It is equal to 80 minus 40 into 100. So it comes around, it will be coming around 75 percentage. So with the help of the lever rule, in this way, we'll be finding the percentage of phases at different temperatures. So this is the use of lever rule with respect to an isomorphous system, which is useful in finding the percentage of different phases formed at various temperatures and at various compositions of alloy. So basically we are discussing about an isomorphous system. In an isomorphous system, we will consider the two metals. If you consider the two metals or two components as A and B, they are completely soluble in the liquid phase, and they are completely soluble in the solid phase. Okay. So for example, if you take copper and nickel alloy system, they both are completely soluble in the liquid and completely soluble in the solid phase, and thus they form a single solid solution. After the formation of the solid solution, you can't differentiate between copper atoms and nickel atoms. The microstructure, if you look at the microstructure of an isomorphous system, it resembles like a microstructure of a pure metal. Okay. Suppose if you consider water plus alcohol, okay, if you mix water and alcohol, they both are completely soluble in each other to any extent, and they form a single phase. Okay. Similarly, copper and nickel system. Okay. Suppose if you consider the mixing of oil plus water, they will not be mixing in each other. Okay. They are not soluble in each other. So basically we are talking about solubility of one component in the other, right? Suppose if you consider silver and gold alloy, okay, they both are also soluble in each other, and they form a substitutional solid solution. So to form a substitutional solid solution, we are having some particular principles. Okay, those principles are known as Hume-Rothery rules. So based upon the Hume-Rothery rules, we can say whether the components in the alloy system can form a substitutional solid solution. The components in the alloy system can be soluble to each other to any extent in the solid state or not. We can identify with the help of Hume-Rothery rules. So let us know what are the Hume-Rothery rules. So first one, crystal structure. First one is crystal structure factor. Okay. So if you take copper, it is FCC, and if you take nickel, it is FCC crystal structure, and they can form a substitutional solid solution. If you take silver and gold, they both have identical crystal structure, face centered cubic crystal structure, right? If you take antimony, okay, if you take antimony bismuth, okay, if you take antimony and bismuth alloy, they both have rhombohedral crystal structure. They both have rhombohedral crystal structure, and they both are completely soluble. They both are completely soluble to any extent in the solid state, and they form a substitutional solid solution. And they form a substitutional solid solution. So with these examples, we can understand the two elements must have, same crystal structure. The two elements must have same crystal structure. Then they can be soluble to any extent in the solid phase, and they can form a substitutional solid solution. Okay. So the first factor is the two elements must have the same crystal structure, okay, in order that a substitutional solid solution can be formed, right? Next, second one is the size factor. Okay. The two elements must not have a difference in atomic radii. The two elements must not have a difference in atomic radii more than 15%. Okay. So the difference in atomic radii must be between 8% and 15%. If the difference in atomic radii is greater than 15%, the two elements cannot form. The two elements cannot form substitutional solid solution. The two elements cannot be dissolved in each other to any extent in the solid phase, right? If suppose if you take silver and lead alloy, okay, if you take silver and lead alloy, the size difference is 20%. The size difference is 20%. They both have same crystal structure. But the size difference is 20%. That's why they cannot be soluble. To any extent. They cannot be soluble to any extent in solid phase. The maximum solubility of lead in silver is 1.5% in solid phase, and the maximum solubility of silver in lead in solid phase is 0.1%. Okay. So the second important factor is size factor. Okay. If the difference in atomic radii is greater than 15%, there will be no formation of substitutional solid solution. Okay. Next, the third one is valency factor. So the two ions, okay, the two ions must have the same valency. Otherwise, if they have different valency, there is a chance of formation of compounds. There is a chance of formation of compounds, and thus we get, different phases, okay. So in an isomorphous alloy, at the end of solidification, we are having only a single phase, that is alpha solid solution. So the two elements which are constituting an isomorphous system must have same valency. The fourth one is the electron affinity factor, or you can also say it as electronegativity difference, electronegativity factor. So generally the electronegativity must be less. If the electronegativity is more, means the elements will try to form compound. And they form a different phase, okay. So if the elements are separated, with large difference in the periodic table, they cannot form substitutional solid solution. Suppose if you consider Na, sodium and chlorine ions, they have a large electronegativity difference and they form a compound sodium chloride. So thus there may be a chance of formation of different phase when compounds are getting formed in the system. So valency factor must be same and electron affinity must be less, or electronegativity between the two elements in the to form the isomorphous system must be less. So in this video we have seen the application of lever rule, and we have seen some examples which constitute the isomorphous system, and we have seen the governing rules to form a substitutional solid solution, which are called as the Hume-Rothery rules. So in my next video we will be learning the microstructure observation of an isomorphous system. So that's all for with respect to this video. Thank you all.